Hello, welcome to my dear students. This is a third live session for the group theory class. If anybody is there, okay, is not there, then I will again recall some uh, basic about the uh, subgroups. So in this, we just recall about the definition of a subgroup and also we have to define some examples of a subgroups and the criteria how to uh, check is a subset is a group or subgroup or not. Subgroup means we have a clearly subgroup means we can say that a subset of a group G, let G be a group with respect to the binary operation star. A subset H of a group G is called a subgroup of this group G if H itself is a group under the same binary operation as the binary operation of a G. We written denote as H less than equal to G is expects H is a subgroup of a G. So this is the notation we have to use in for say that H is a subgroup of a group G. So that means it simply say means we have a G is a group. Then we choose a subset of this G. And if this subset itself is from a group under the same binary operation, then we can say that this H is a subgroup of a G over the same binary operation. For example, set of integer is a subgroup of a set of a real number and complex number under the binary operation is addition. Because that containing R and also in C and this R is a subgroup of a C because R is a subset of this C and this is a clearly is a under this addition R is a from a group, so this is a subgroup of a C under addition. Now if we have a if you remember in the last we have to decide show that this is by the KLA table this G is equal to 1 minus 1 I minus y and this is form a group under the multiplication and if we take a one subset is H is equal to 1 minus 1 then this H is a subgroup under multiplication because if you draw a table of this 1 into 1 is equal to 1 1 and 1 into 1 is 1 1 and minus 1 is here is a self inverse, so that means you can say that this satisfy all the properties of a group. So H is clearly the subset of a G, then H is a subgroup of a G. Now we have to then we say that some one remark is there that every group G with at least two elements with all the way have at least two subgroups. Every group has at least two elements will always have at least two subgroup, namely G itself and the subgroup consists on the identity element. So if we have only identity element is there, sorry. So identity element is H is equal to A. This is the subgroup of a G. And if we have a G itself is also every subset is a every subset is a set itself also. So this means G itself is a subset and G is also a form of group. So G is itself is a subgroup. So the group H is only containing the identity element and that group is called is a trivial subgroup. This is a clearly subgroup and this subgroup is called is a trivial subgroup. So a subgroup H is called is a proper subgroup of a G, a proper subset of a G is called is a proper subgroup. So if it is not a trivial subgroup, then we can say that H is a proper subgroup. So many examples we have illustrated upon this point. There exist others beside the trivial and improper subgroups. Set of positive real number under multiplication is not a subgroup set of real number and addition. Why? Because we have to, this is a clearly, this is a addition, the set of real number and addition is a group. If we take this set a positive real number, but we have to changing the mm, binary operation is multiplication. So clearly, but because by definition we have uh, a subset of R, but this is not a subgroup because the binary operations are different. So we take a two different binary operation for the group G and group H. So this means we clearly say that this is not a clearly is not a subgroup of a given group G. You note that this is already we have to prove that U8 is a be a group under multiplication modulo 8. Now we take a subgroup H is equal to 1 3, yeah, or 1 5. H is equal to 1 5 is a subgroup of a G. Y is a subgroup of G. You just check 1 into 1 is equal to 1 into 5. 5 if 5 into 5 is equal to 25 divided by 8 is equal to what? So 1 is a self-inverse and 5 is also is a self-inverse. So this means H is equal to 1 and 5 is a subgroup of a group G. The identity element 1 is 0 and this is clearly 1 is a 1, inverse of a 1 and inverse of 5. So every element X belongs to the H. X, this is the by the KLA table. We can show that this is a clearly identity element is there and then inverse of a 5 is equal to 5, inverse of a 1 is equal to 1. So this means clearly this set H is equal to 1, 5 is a subgroup of a G. Now, my question is this: Can what can about say that is equal to 1 and 7? Is a 1 7 is a subgroup of a, or H is equal to 1 comma 7 is a subgroup of a G or not? So, for example, if you say that H is equal to 1 comma 7 is a subgroup of not. Now, for this we check is a 1 into modulo 8 is equal to 1. So this is clearly 1 into 1 is equal to 1. And you have a 7 into 7 is equal to, you have a 79 and then you have to multiply it by 8 is equal to 1. So this is clearly can say this is a subset of a this. And now you see this is again satisfy this. So in place of a 5 we put a 7 and then 7 is the same itself and then we can say that clearly this H is equal to 1 comma 7 is also is a subgroup of a G. Similarly, we can say that about what about the 1 comma, if we take H is equal to 1 comma 3. Now here is a 1 into 1 is equal to 1 and also 3 into 3 is equal to 9 divided by 8 is equal to 1. So there is a we have a this is equal to one of the subgroup. Then you have to say that we can say that H is equal to, you have a 1 5, 1 3, 1 7. These all are the subgroup and H is equal to only 1 is also a subgroup and U8 itself is a subgroup of the. So these are the all trivially is a subgroups of a this set. So now we have to, you know, that we have already discuss about the group of a general linear group for this is LNR. We denote it be the set of all n by n invertible matrices, and then we define a SL2R, SLNR also, and then this if A is the element of a GNR, then determinant of A is equal to 1. Here determinant of A is not equal to 0, so we collect the all the matrices where determinant of A is not equal to determinant of A is equal to 1, and then clearly you can see that this SLR is a subset of a GLNR because GLNR be a collection of all invertible matrices where determinant of A is not equal to 0, but SLNR is a collection of those matrices where determinant of A is equal to 1. So SLNR clearly is a subset of a GLNR, and then this GLNR is a group under the multiplication. So SLNR is also a group of under multiplication. So SLNR is special linear group. SLNR is called is a special linear group. So a special linear group LNR is a subset of subgroup of a GLNR. So this SNR you can use this satisfy the clause because determinant of AB is equal to determinant of A into determinant of B. Determinant of A is equal to 1, determinant of B is equal to 1, determinant AB is equal to 1. Okay, you can just say check into this form. We can say that is closed or not. We can say that we take any two element A comma B B in SL R. So then clearly you can say that determinant of A is equal to 1 and determinant of a B is equal to 1. Then we know that determinant of a AB is equal to determinant of A, determinant of a B, and this is equal to, you have a 1 into 1 is equal to 1. So this implies that AB in SL and R. So this is clearly is closed and also inverse codeterminant is equal to 1. So we can just satisfy all the properties of a group. So SL and R is clearly is a subgroup of a general linear group, and SL and R is called is a special linear group. So now this way we can just say that AB in SL and R. Identity matrix surely has a determinant 1. So A is the element of this, then determinant of A inverse is equal to 1 upon determinant of A is equal to 1. So A inverse is also belongs to the SNR. So this means we can say that SNR is a subgroup of a GNR and called as a special linear group. So as I told you, this group is called as a special linear group. Now I take some different type of example. One this example we can say that S is equal to, we have a 0 comma 2 of Z4 under addition is a subgroup or not. Clearly we can say that if this is a clearly this is a subset of a Z4. The element of a Z4 are the element of a Z4 are the 0 to 1 to 3, and 0 2 is clearly the subset of a Z. Is we clearly form a by the Keller table you can say this is a 0 and 0 2, so, and then we have a 0 2. So 0 2 2, the inverse of a 2 is equal to 2 and 0 is itself inverse. So this is satisfy all the property, and this is a clearly proper subset of a Z4. It is only the proper subgroup. This is the only proper subgroup of Z4. Why we can say that? Then another set we have a 0 1. 0 1 is not a clearly not a subgroup. Why? 1 plus 1 is equal to 2, and 0 1 3, and then you have 3 1 plus 1 is equal to 2. So this is again S is a group because it is closed. So 0, and this is contain the inverse, that is 0 plus 0 and all is equal to 0. So this is clearly, we say that this S under multiplication addition modulo 4 is a group, and so this is S is clearly is a subgroup, and this is a proper subgroup. And if there is a no, suppose H is any other subgroup of a Z4 and one is in H of this. If one is belongs to the H, then 1 plus 1, 1 plus 1 plus 1 and so on, and 0. So this H is equal to clearly you have a Z4. So there is only possibility you have a Z is H is equal to Z4. So this means we can say that this 0 comma 2 is the only proper subgroup of this. There is no other proper subgroup. If you see, you cannot find any other proper subgroup of a this group Z4 under addition modulo 4. So this is the only proper subgroup of a this thing. Okay, similarly, if we have a 3 is in H So we have there is a possibility is there. We H is a so under addition is any other proper subgroup. So if H and one belongs to the H, then so 1 plus 1 is should be there. 1 plus 1 plus 1 it should be there, and 0. So H is equal to clearly is a Z4. 1 plus 1 is equal to 2. 1 plus 1 plus 1 is equal to 3 and 0. So H is a Z4. Similarly, if we take a 3 is in H, so 3 plus 3, 3 plus 3 plus 3 and 0, then again we have a 3 plus 3 is equal to 6 is equal to 2, 3 plus 3 plus 6 is equal to 1, then we have a 0, and so H is equal to Z4. So again H is not a proper subgroup. So we have only one proper subgroup for this is equal to the only subgroup of Z4 are 0, S and Z4 itself. So this Z4 has only three subgroups are there. One is a proper subgroup S, another is a trivial subgroup 0, and Z4 itself is a subgroup. So this means we can say that clearly we have a these three subgroup of this Z4 under addition. Okay, now we have to there's a we have to check each and every steps one by one for showing that the group any subset of a group G is a subgroup. So there is any result. So we have to uh, mm, we can say that this lemma, and this lemma says that if G is a group and H is a subgroup of a G, then the identity element of a G and H are the same. We can say that identity element of a G and H are the same because identity element of a group is a unique, and if H is a subset of a G, then the group H is itself is a subgroup. So only subgroup only possibility is there. Identity element of a G and H are the same, and if H inverse of a H belongs to H, then the inverse of a H belongs to G are the same. So because of the subset, inverse of each element is a unique. Inverse of each element is a unique. So by this property, we can clearly say that if H is the element, inverse of H is H, then inverse of H belongs to G are the same. Proof, let EH denote the identity of H, and EG denote the identity of a G, and H is the element of a H, and this is subset of a G clearly. So H into EH is equal to H by the property definition of a uh, EH is the identity element of H, and then we have a H is the element of a G also. So H into the identity element of a G, EG is equal to also H, and then we have a EH is equal to H and EG is equal to H. Then we can say that by the EGH is equal to now cancellation, by the cancellation law, apply the cancellation law, we can find that GH is equal to Hg. So this means we can say that the identity element of a G and identity element of H are the same element. Similarly, for the second part, for proving, we have to say that H is the element of a H. Suppose H1 denote the inverse of a H in H, and H inverse denote the inverse of a H in G. So we have to take H1 denote the inverse of a H in H, and H inverse denote the inverse of a H in G. So H1 can be written as a H1 into H inverse because H1 can be H into identity, and identity H is the inverse of a G. So that means H into H inverse is equal to identity, and by this H1 H inverse and H1 is denote the inverse of a H in H. So if H1 is the inverse of a, this means this is equal to identity again, and then this is the identity E H inverse, then this is equal to H inverse. So H and H inverse are the same. So thus the inverse of a H belongs to H and the inverse of H belongs to G are the same. So this complete the proof of a this result lemma. Now let us examine some criteria for determining exactly when a subset of a group is a subgroup. So this is the theorem. There is no need of a check each and every steps of a if H is a subset of a group G, then we can say that H is a subgroup of a G. If and only if a subset H of a group G is a subgroup of a G if and only if these conditions are satisfied. One is H is a non-empty, and if H1 and H2 are the element of H, then H1, H2 is the element of H, means H is a closed, and also every element inverse of each element belongs to the H. So if we say that if we have to satisfy only these conditions, H should be non-empty, and H is closed under binary operation, and every element has inverse is also belongs to the this set H. Then we can say that then H is a subgroup of a group G. So I'm not going to prove this because I already proved into the this. Now we have to try to some example by this. We know that Z at under addition form a abelian group under addition modulo 8. Now we take a 0, 2, 4, 6, H is equal to this. So we say that H is clearly non-empty. One condition is satisfied of the theorem. Second, say that you have to check any two elements. So of this, we take a draw the carry table for this set H. And now you see we have to just say that this body of a this clearly every element of a this set is the element of a this set H. So H is a closed, clearly H is a closed under this addition modulo 8. So H is a closed. So now we have to, if H is a closed, so we check is every element has an inverse. The inverse of a 0 is there, inverse of a 2 is a 6, inverse of a 4 is itself, and inverse of a 6 is equal to 2. So every element has the inverse. 2 is the element of H, then inverse is also belongs to the H. So clearly this means we can say that this H is a subset, and this is a proper subset of this set G and Z8. So this is a so clearly this is a subgroup of a this G. So by the Cayley table, we can say that this is a clearly is a, and also this is H is a non-trivial abelian subgroup of Z8 under the addition modulo 8. Okay, now Z10 and under multiplication modulo 10 is not a group under multiplication modulo 10. Because Z10 is why does Z10 is not under multiplication modulo 10 because Z10 is the element of a Z10 is equal to 0, 1, 2. The inverse of a 0 does not exist here. Clearly under multiplication modulo 10, and so Z10 is a close under multiplication modulo 10. One is the identity element is there. However, Z10 is not a group with respect to the multiplication modulo 10, since some of its element do not have an inverse. For example, if we say easy to show that 4x is equal to identity element is equal to 1, and then equation is this 4 into x. X is some element in the Z10 we have to find and has a solution of in Z10, and then you can say there's 10 and 4 as GCD of this is equal to 2, not equal to 1. So this means this equation has a clearly is a no solution in mod Z10. So this equation is a no solution. Then some of the element of this Z10 has a no inverse into the, but one is the element is 0, does not have an inverse. Then you can just check is equal to 2, and you can find in this set there is a no element into the 0 to 9 multiplied by 2 giving you have a 1. So that means you can say that clearly this is satisfying to this one. Now we have to analyze the multiple table for the subset H is equal to 2, 4, 6, 8 of Z10. Now in place of a Z we have to take a 2, 4, 6, 8 and then we have a like this. You can see this set. Then this is a clearly you can see all this. You see all the element of this body is clearly is closed. Surprisingly, the table 6 reveals that the 6 serve as the identity element of a H, and H is actually constitutes a group under the multiplication modulo 10. However, it is important to note that H is not a subgroup of a Z10, as Z10 is not a group under multiplication modulo 10. So if we take this is clearly you can see here. This 6 serve as a identity element of this set. So this is H is clearly subset of a Z10, but we can say that as this Z10 is clearly is not a not a group. So clearly H is also is not a subgroup of a this thing. Now we have a another criteria. We have to combine the last two properties together. H is non-empty, and we have a close and inverse can combine into this form. X and Y is the element of H. H implies that XY inverse is also the element of H. Then we can say that that G be a group. H is a subset of a G. Then H is a subgroup of a G if and only if H is a non-empty and XY belongs to the H, implies that XY inverse is also belongs to the H. So if these two properties hold, then we can say that any set is these two properties hold, then we can say that H is a clearly H is a subgroup of a this group. Okay, so now we have to prove. I am not again prove this. So I just skip the proof here because proof is already I explain you into the class. Now this is very important to realize that if a group is written addition, then the condition x, y, x inverse belongs to that becomes x plus y minus x and x minus y into the h. This is the way. So n we have an example. If n greater than equal to 0, we can write nz is equal to ns. S is the element of a z. So the identity of a z is clearly is equal to 0. 0 can be written as a n into 0. So this means this clear if x and y is the element of a nz, then x is the element of a ns, y is the element of a nk, s and k are the element of a z. Now we show that x, y inverse is also belongs to the nz. So under addition, we have to say that x plus y can be written as a n s plus k is the s and k are the element of a set of integer. So sum is also an integer. So n into s plus k is the element of nz, and minus nk can be n into minus s. So this is also the element of a this. So this will satisfy all the properties of a this. So nz can be written into the form nz is a so or we can just if you want we can use the previous condition also. So we can write in the this is x minus y can be written as a n of s. We can write plus n of minus r. We take r, then we can say that n is common. We can say that s minus r, and s and r is the element of a z. So this s and r is the element of a z. So this is clearly is equal to n. This is n is z. So x minus y into nz. So this is identity. So clearly we can say that a 0, and this means h this nz is non-empty by this property, n is a non-empty, and by this property this previously we can say that this is a set is a clearly satisfy all the properties of a subgroup. So this is a clearly nz is a subgroup of a z set of integer. Our next criteria is quite interesting. It is obvious reduce the number of things that is a one need to check, but it is only work for a finite subset of a group, not all. This is a, if H is a finite non-empty subset of a group G, then H is a subgroup of a G if and only if H is a closed. If we have a finite subgroup, then if we have a group is a finite, then H is a finite non-empty subset of a group G, then H is a subgroup if and only if H is a closed. So we have to only check if H is a closed under the this binary operation, then we can say that this set is a clearly is a subgroup of a G. So proof again, according this review class, we have no need of a proof all of them. So we just skip the proof and just emphasize on the some examples. Okay. Now H is equal to Kz belong to the Zn, X is the element of a Z. H is clearly non-empty because at least 0 is the element of a Zn. So now we have a Kx plus Ky, and then can be Kx plus Ky can be K of X plus Y. X is the element of Z, Y is the element of Z, X plus Y is also the element of Z. So this means this is the element of a H. So therefore H is a clause under the addition in Zn. So Zn is a finite, and theorem, previous theorem is showing that if we have a H is a non-empty and closed, then it's under the binary operation, then we can say that this is clearly is a subgroup of a this finite group G. So Zn is a finite, and therefore by this H is a subgroup of a this Zn. Now we next we discuss some special types of a subgroup that has natural allies within any group. We will explore how this new subgroups can be derived from the existing one. First is a, if a intersection of any two subgroups of a group G is also is a subgroup. So we have to just say that we say that we have an intersection of any two subgroup. So we take intersection in any two subgroup. We take a any two intersection of any two subgroup of a G is a subgroup of a G. If we take intersection of any two subgroups, then we show that of a G, this is also is a clearly this is a subgroup again. Proof, let H and K be a two subgroup of a G. So H and K are two subgroups of a G, then H is K are closed under addition, and also every element has a inverse also belongs to this set. Now we have to show that H intersection K is also is a subgroup. So we show that HK by the theorem, we can say that X and Y is the element of a H intersection K. Then X Y inverse is also the element of a X H intersection K. So E is the element of H, E is the element of a K also. So E is the element of H intersection K. That means H intersection K is clearly is a non-empty. At least one element should be belongs to the there. And then we can take any two as element. AB is the element of H intersection K. So AB is the element of H and AB is the element of a K. And AB is the element of H means H is a subgroup of a G. Then AB inverse is the element of H. And since H and K are subgroup of G, so AB inverse is the element of H, and AB inverse is also the element of a K. So AB inverse is the element of H and AB is the element of a K. Then we can say that AB inverse is the element of a H intersection K. So this H intersection K satisfy all the properties of our theorem. Then we can say that clearly this set, if H and K are two subgroups, then H intersection K is also is a subgroup of a group G. And this can be extend for a finite number of a collection of a index I belongs to the this be the collection of a subgroups of a group G. Then intersection of all the finite collection of HI is also is a subgroup. The proof is similarly by the previous one. Now next is very interesting. We have a this we can say that the union of a subgroup is not always a subgroup. Now the next question is this: what can say about the when the union of a two subgroups is again is a subgroup? Think about this in 2 minutes I give, and think about the example of for a subgroup. Union of a two subgroup is not always a subgroup. Means you have to find a group and take a two subset of this group should be a subgroup, and then take a union, this should be not a group. For example, we take a set of integer under addition is a group, set of even integer under addition is a group, and set of 3z is clearly is again is a subgroup. So 2z under addition and 3z under addition is clearly is a subgroup of a this G. Now we have to check is a two unions 3z 2z union 3z is a subgroup or not. Check, verify that, and tell me which condition is not satisfied for this case. You see, we take a 2z types element, but in the union is what types of element of the union? 2z or 3z types element are there. So 2 comma 3 is the element of a 2z union 3z. When we take it sum of these two, 5 is equal to this is not belong to the union. So in 5 is does not belong to the here, and 5 is also not here. So this 5 does not belong to the 2z union 3z. So this means 2z union 3z is clearly is not a subgroup of a group G. But union of a subgroup. But the next question why I ask you, when we can say that the union of a two subgroups should be a subgroup. So union of a two subgroups H and K of a group G is a subgroup if and only if either H is containing of a K or K is containing into the H. If one of the subgroups containing into the other, then only in the case we can say that H union K is a subgroup of a G. So by the result, the union of a two subgroups of a group G is a subgroup if and only if one is contained the other. Okay, let proof. We can say that actually new. Let H and K be two subgroups of a G such that one is contained the other. That is either H is containing K or K is containing H. So here is H union K is equal to K, or H union K is equal to H. So K and H are the subgroup of a G. So if H union K is equal to K, then H union K is a subgroup, and H union K is equal to H, then H union K is a subgroup. So this means H union K is a subgroup of a G. Now one way is trivial. Now we have a, if we say that H union K is a subgroup of a G, then we can say that either H containing G, K, or K is containing into H. So we have to prove that. Suppose H is not containing K and K is not contained in H. So we just say that there is a negation. H is not contained in K and K is not contained in H. Then there exists an element A and B. A is the element of a H, but A is not at the element of a K, and B is the element of a K, but B is not at the element of a H. So we just say that H take any two elements, and then these two elements is clearly say that A is the element of H and E does not has the element. B is the element of K and B does not has the element of a H is there. Clearly A, B is the element of a union B, H union K. Since H union K is a subgroup of a G, so A and B is also the element of a H union K. And if AB is the element of H union K, means AB is the element of H or AB is the element of a K. by the proper definition of a union. So we can say that there is a two case if AB is the element of H and AB is the element of K. If AB is the element of H, and since A is the element of H, A inverse is also the element of H, thus A inverse A, B is the element of H, which is a contradiction over 6 because B does not belong to the H. Now similarly, if AB is the element of a K and B is the element of a K and K is a subgroup, so B inverse is also the element of a K, then we can say that AB A inverse, AB B inverse is equal to AB B inverse is identity is equal to A is the element of a K, and then we can say that which again by the our fifth A does not belong to the K, so we can say that clearly, which is contradiction. So this means our assumption that H is not contained in K or and K is not contained in H is wrong. So this means either H is containing K or K is containing into H for this. So this completes the proof of a this theorem. Okay, next is what is the center of a group? The center of a group, generally we denote it as a ZG, is the set of those elements in G that commute with every element of a G. That is Zg is equal to G is the element of a G, Gx is equal to Xg for all X. Means collection of those element of a G which commute every other elements of a G. This is called the center. Zg is said to be the center of a group G. Consider Z is center, G is equal to Z under addition, and G is a abelian group. Therefore, every element of a G commute with all other elements of a G. So center of a G is nothing but is equal to G itself. Means whole Z is the center of a G into this. Means every in this case we have a every element should be commute in this case. Now we have a question is this. Think about this. I give you a few minutes. Just try to solve this question. Find the center of a GL2R. GL2R is a general linear group, and you know that general linear group is clearly a set of a or 2 by 2 invertible matrices, and then this is a clearly is a group, and then you have to find the center of this. Find all those elements which are commute with this set collection of this set. So, think about this is a I give you 2-3 minutes and then we have to then I try to solve this problem. Okay, let's try. We try this. To find the center of a GL2R, we need to determine all matrices A belongs to the GL2 such that AB is equal to BA for all B belongs to the GL2R. So A is equal to A, B, C, D. We have to take determinant of A is not equal to 0. For A is in the center of a GL2R, it must be commute with every element of a B is equal to E, F, G, H belong to this. This means that AB is equal to BA. So AB is equal to, we have a like this, A, B, C, D, and then we take a multiplied of this, and BA is equal to these should be equal. And if these two equal means we have these are the four conditions should be equal. This A, B, C, D equal to E, A, F, G. So this is one condition. This is the second condition, and this is the third and fourth condition are there. So this gives the following system of equations. We have a 1, 2, 3, 4 system of equation, and now since these equation must hold for all choices of a E, F, G, H, we analyze this is equal to this consisting E is equal to 1, and f is equal to 0, g is equal to 0. So we get a is equal to a, which is always true, and b is equal to 0. Now second condition we just choosing e is equal to 0, f is equal to 1, and gh is equal to 0. Then we get 0 is equal, b is equal to 0, and confirming b is equal to 0 from above also. Now third condition is equal to this. We have to e is equal to 0, f is equal to g is equal to 1, and h is equal to 0. We get c is equal to 0. Here c 0. Then we have a this is equal to g is equal to 1. So d, and then we can just say that c is equal to, we have a 0. F is equal to, we have a 1. So a is equal to d, and b, this is 0. So a should be d, means we have a determinant. Okay. Now we have a this is equal to this, choosing E, F, G, H. Then in this case, D is equal to this, V, H, which is always true. So A is equal to A, D is equal to D, and B and C are 0. So we have a matrix like this. So B, C is equal to the remaining entries of A and D must be the matrix is this form. A, D, B, 0, 0. This commutes all other matrices of a GL2. For this, this is true. A must be equal to D. So hence A is equal to D. So this means we can say that the center of a G is the form of this times lambda I, lambda, lambda, 0, 0. So Z as center of a GL2R is the form of this form. So this is clearly center of a this way we can calculate the how to find the center of a any matrix. By this method we can calculate the center of a, so this way we can just calculate the center of a GL2R. Okay, now the question is this: is a center of a G is a is a subgroup of a G or not? Think about this. There is the result. We can say that this is a proof. So if we have to show that E is the element of a center of a G, E is clearly commute every other element of a G. So this means we can say that this center of a G is clearly is a non-empty. So center of a G is clearly is a non-empty. So first condition is satisfied. Now we take any two elements of a center of a G. A and B is the element of a center of a G. Then we can show that AB inverse is also the element of a center of a G. And if a success to satisfy this condition, then we can say that this is a subgroup of a group G. So EG can be written as a G into G. So E is the element of a G, so clearly is a non-empty. Let X and Y is the element of a this, and G is the element of a G. So X, Y inverse G is equal to same as a X, Y inverse G into E. And now X, Y xy inverse G can be written as a G times xy inverse. So then we can say that xy inverse is element of a ZG. So G can be written as G into E. G is the element of a G. E is the identity element. So G can be written as a G into E. So xy inverse X, and G X and Y is the element of a this X means Y is the element. Y inverse is also the element of this. So we can say that right in this form, X Y inverse Y is the element of a ZG. So YG is equal to GY. So this is GY is the same as a YG. So YG. Now this can be written as X and X. This is equal to identity element. So X E G Y inverse. Then you have X G Y inverse, and then we can say that again X is the element of a ZG. So XG is equal to GX. So this is equal to GXY inverse. So xy inverse G is the same as the gxy inverse. So then we can say that xy inverse is the element of a zg. So this means this complete the proof of this result. We can say that the center of a G is a subgroup of a G. So center group is a subgroup of a G. Now what about this? Let G be a fixed element of a group G, and if H is equal to A is the element of a G, AG square is equal to G square A, and K is equal to GA is equal to AG. then H is a subgroup of a G and K is a subgroup of a H. Think about this. Let's think about this 2 minutes about this question. Okay, let us try. We show that H is a subgroup of a G and K is a subgroup of H. So we think about that AB is the element of H. Then AG square is equal to G square and BG square is equal to G square B by the the given condition. Now ABG square is equal to B into G square and B into G square is equal to G square B. AG square is equal to G square. So the AB G square is equal to G square B. This AB is the element of H and AB is the element of A. Then we can say that AB is the element of a H. As for all AB is the element of H. And now we just say AB is AG square inverse is equal to G square A inverse. Then G square inverse is equal to A inverse G square. This is not equal to sign. This is a we use the product rule here. This is by mistake. This is not. This is this type product. This can using the property of AB ka inverse is B inverse A inverse. So G square inverse A inverse is equal to A inverse A G square. Now G to the power minus 2 A inverse and A inverse G to the power 2. This implies that A inverse G2 is equal to G2 A inverse and hence A inverse is the element of H. Therefore H is a subgroup of a G. Now next is you have to show that in the similar fashion K is a subgroup of a H. So I just leave this verify that K is a subgroup of H is a in the similar fashion you can try for I just leave this for your homework. Now one more example. If H is equal to we have a B 0 1, A is not equal to 0 and B are the some real number is a subgroup of a multiplicative group of a 2 by 2 non-singular matrices over R. So think about this problem is so let G be a multiplicative group of a 2 by 2 non-singular matrices over R. So we have to show that H is a subgroup of this G. So A is the element of a A1, B1, 0, 1 belongs to the H. B is the element of A2, B2 and 0, 1. These are the element of H. Clearly A1 is not equal to 0 and A2 is not equal to 0 and A1, A2, B1, B2 are the elements of a R. So now we just take this is a because this is a finite. So we take a B inverse. First take B inverse. B inverse is nothing but is equal to we can say that A2 ka inverse, B2 ka inverse, 0 and 1 ka inverse is this itself. And then we have a since B inverse is equal to identity. So B inverse, so AB inverse is equal to we have a this and this is the clearly that is the similar type of elements. So this is we can say that AB inverse is this is the element of a H. So clearly H is a subgroup of a group G. Okay, now we have to one more problem. G cannot be have a subgroup of H with H is equal to order of H is equal to n minus 1 where n is equal to order of a G should be greater than equal to 2. If such subgroup H does exist, then it must conclude exactly one element G from G. Since H is order of H is greater than equal to 2, so we can take a non-identity element H belongs to the H. Now consider the element of a GH. If GH does not belongs to the H, then GH is equal to G, and by the cancellation implies H is the identity, which is contradiction, because we have to take there is a two elements, and H should be not the identity element. On the other hand, if GH is the element of H, then GH into H inverse is equal to G is the element of H. Again is a contradiction, because G is not G is the element of a G is H. So subgroup H does not exist. So this means we have to say that such a subgroup does not exist. Next is we have a important concept about the cyclic group, and the cyclic group we say that is a group element. Let G be a group and G is the element of a G. If G can be represented as a G to the power n, G, and n is the element of an integer, we take as multiplication n times, then G is called as a cyclic group, and this is generated by G, and it is denoted by the bracket by G, and where G is called the generator of a G. Simply you can say that we have to find a one element. In other simple language, a cyclic group means if we have a G is a group, and in this group we have to find a one element from this set G, and if under the binary operation, whatever addition we have to add this. If you have multiplication, we have to multiply this. So if we have a certain element like this in the set, if such as element is exist, so we can say that if such element we can find in this set such types of element, so we can say that clearly if such element is exist, so one element can generate whole the
Charging your Mac.
all the elements of the groups. So if all the elements of a group generated by the single elements, then this group is called as a cyclic group, and the element which generate whole the elements of this group is called the generator of this group. Simply I just said that if we have a in multiplication we have to written G to the power n. If a group G is written additively, then the power G becomes the Ng. As added, we have to add G plus n times. So we have to simply say Ng types elements. Under addition is this notation. Under multiplication is equal to this way we can say that. And from the definition, it is clear that if generated by G, then also generated by G inverse. G is G to the power n, the same as G inverse, n is the element of a Z. So G to the inverse to the power n, so this is generated by G inverse also. Now we have two example. We have a set of integer. Now check is a cyclic group under addition. Indeed, Z is generated by 1. So we go nz, we have a 1 plus 1 plus 1 and so on. So if we have a 1, n is equal to 1, n is equal to 2, 3 and so on. This is giving where we have a, so n is the generated by 1, and Z is equal to is a set of integer is a cyclic group generated by 1. Then but there is no other element you can find in this Z except 1, which can generate the whole group element, and also minus 1, because n can be written as a minus n into 1 minus 1. N is the element of a Z set of integer. So this set of integer is a cyclic group, and it has only two generators. One is 1, another is a minus 1. Now additive group Zn, we take a 0, 1 to n minus 1, n is greater than equal to 1 is a cyclic group under we have a addition modulo n. And now we check is this clearly given Rzn. R can be written as R into 1 is a multiple of a 1. So R is the by the 1, and Zn is generated by 1. And if G is any group, E is equal to is a cyclic group, is only identity element, then this is clearly the cyclic group. Now we have to suppose this group, we have to multiplicative group plus minus 1 plus minus I is a group of a complex fourth root of unity. And then G is a cyclic, and the generator of this 1 is not a generator, because by 1 can be 1 into 1, 1 into 1 cannot retain any power, we cannot getting I is there. So 1 is not a generator is there, minus 1 is not as a generator is there, I is a generator is there, because I into I to the power 1 is equal to I to the power 2 is equal to, you have a minus 1, I to the power 3 is equal to, you have a minus I to the power 4 is equal to, you have a 1. So in this case, you can say that clearly I to the 0 1, I to the power 1 is equal to I square is equal to minus 1, I cube is equal to minus I. Then this generate all the elements of a G. So I is generator of this cyclic group. And because you know that in this set, I and minus I is the inverse of each other. Inverse of I is equal to minus I is the inverse of I. So this means minus is I also is a generator of this group G. So this group G has only two generators, is I and minus I, and this is clearly this group is a cyclic group. So this is clearly G is equal to plus minus 1 plus minus uh, I is a clearly is a cyclic group. So cyclic group may have a more than one generator. However, not elements of a G need to be a generator. Now, for example, minus 1, 1 and minus 1, and clearly not is equal to G. So minus 1 is not a generator, and similarly 1 is not a generator. Now we take a group G is equal to U7, and now as a indeed what is generated by 3, because the element of a U7 is equal to 1 uh, 2 3 4 5 6. So 3 to the power 0 is equal to 1, 3 to the power 1 is equal to 3, 3 to the power 2 is equal to 9 divided by 7 is equal to 2, 3 to the power 3 is equal to 10, 27 divided by 7, remainder is equal to 6, 3 to the power 4, remainder is equal to 4, and so on. This is 1, 2, 3, 4, 5, 6, all element G is generated by this. Now my question is different. Can you find any other element is also the generator? We have a 3 is a generator of this cyclic group. Can you find this is a cyclic group and the generator of this group is equal to 3? Can in this U7 you find any element which can generate the whole set? For example, 2? No, because 2 to the power 0 is equal to 1, 2 to the power 1 is equal to 2, 2 square is equal to 4, 2 to the power 3 is equal to 8 is equal to 1, then repetition is starting, and 2 to the power